Hello, my name is Dan Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And today I'm going to be going through the SparkFun Inventors Kit guide with you and doing Project 1, which consists of 4 circuits. If you are a current student with taking Comp 444 with Athabasca University, you will have this guide, and you will have also gotten this SparkFun Inventors Kit, which comes with a RedBoard, which is a generic Arduino compatible microcontroller, a breadboard, and all of these other components, which are various sensors and actuators and just a lot of fun stuff you can fool around with and have fun in your adventures with microcontrollers. So this is the SparkFun RedBoard that comes with the kit. So it's just a generic Arduino type microcontroller, and in the guide it shows you how to mount on this plastic mount and along with the breadboard. Also, you'll notice here that I have a different microcontroller set up with some other components. So this is a generic type microcontroller called made by Elegoo. So again, it's just an Arduino type microcontroller, just like the RedBoard. They work exactly the same, and as the breadboards are very similar. I just bought this kit that included this microcontroller along with a bunch of sensors, 37 sensor kit, off of Amazon for maybe $75, just so I could go beyond what the course does with the kit. But the kit will have everything you need to do the projects associated with this course, which takes you from blinking an LED to making a remote control car. So without further ado, let's get right into it. So what I'm going to talk about in this video today is I'm not going to go through the entire SparkFun Inventors Kit guide. I'm just going to kind of briefly go up to about page 35 and talk a little bit about the breadboard itself, the RedBoard, which is the Arduino microcontroller board that comes with the kit, as well as the first project. And the first project consists of 4 individual circuits that we're going to be making. So the first one is what's highlighted in yellow here, and basically it introduces you to blinking an LED, demonstrating the digital output in a simple yet effective way. So we're going to upload code that makes the LED flash on and off. That code is available on the SparkFun Inventors Kit website, which is referenced in the guide. And this is kind of like the hello world of the Arduino programming language. So if you've done any programming before, you'll be very familiar with the fact that in any programming language, the first program one typically does is a program called Hello World, where you output the text Hello World to some console. This is kind of the quintessential first example or first program that anyone does when learning a new programming language. However, because Arduino is a hardware-based programming language where you're not doing so much graphical programming, instead you're programming to affect hardware in the real world through the microcontroller, the hello world of the Arduino is just flashing or blinking an LED. In fact, most Arduino compatible boards come with the blink program already installed by default. After we do that first program, we're going to move on to circuit 1B, which incorporates a potentiometer, which we'll use to adjust the brightness of the LED. And a potentiometer is just a variable type resistor. And if you're not sure what a resistor is, well, that's just a component that resists current flow in a circuit, helping to protect sensitive components like an LED. So a potentiometer is a variable type resistor where we can actually adjust the resistance via a knob or something like that. And that'll also help us get a little more understanding of analog input. After that, we're going to move on to circuit 1C, where we introduce a photoresistor, which will enable our circuit to respond to changes in light level. So just like a potentiometer is a variable type resistor that we, the user, can control the resistance of by turning a knob, a photoresistor is also a variable type resistor, but we don't control it directly. Instead, a photoresistor, the resistance of the component itself changes based on ambient light levels and how much light is getting on the component. And that type of technology is actually what's used if you have a night light in your child's bedroom or something like that that turns on automatically when you shut off the lights. It's most likely operating via a photoresistor. And then finally, we're going to move on to circuit 1D, where we create a multicolored RGB nightlight. RGB stands for red, green, blue nightlight, which is essentially, you know, 3 LEDs in one. And by through some clever programming, we're able to, you know, basically create a wide array of colors with a single LED. And we're going to incorporate in that project what we learned from the photoresistor project and the potentiometer project. So without further ado, let's start. So I'm going to skip past a lot of the stuff in the SparkFun Inventors Kit and just go straight to the project stuff, because this kit is very well laid out and you're going to want to read this in its entirety anyway if you're taking the course. So I might mention a few highlights here and there, but for the most part I'm going to go through pretty quick. So again, this booklet has information on how to build 5 projects, which are a total of 16 circuits altogether. So in today's video, we're going to be going over one project which has 4 circuits involved. And the core philosophy of this guide and of SparkFun in general is that anyone can and should play with electronics. And it's never too early to start, you know, within reason, of course. So we're going to be discussing today Project 1 Light, which is going to take us up to the end of page 35, I believe. And again, we're going to be blinking the LED using potentiometer, photoresistor, and creating an RGB nightlight. A lot of the rest of the first part of the guide just explains a little bit about the RedBoard, which is again just a generic Arduino compatible microcontroller. And what is a microcontroller? Well, it's basically a small portable computer. It's capable of taking inputs such as, you know, reading a push of a button or reading a sensor, and then interpreting that information and then controlling various outputs like blinking an LED or spinning an electric motor. It basically allows you to interact with the physical world, so it's called physical computing. This microcontroller can read sensors, which are, you know, getting data from the physical world, and it can create, you know, it can affect actuators, which, you know, turning on LED light or moving a motor. So it's what's known as physical computing. I'll zoom in here on this a little bit. I noticed it's probably a little hard to see. Again, this guide just talks about a couple things specific with the RedBoard, such as that it's based off the Atmega 328 microprocessor as our most Arduino compatible boards. And what that really means is, if you look at the RedBoard, there'll be there's a lot of different microchips and just little components on the board itself. So like you'll see chips here and a microchip here, and these things are what are actually the brains behind the development board. So these are known as a development board rather. But a lot of it you can see is empty space. It's just to make it more convenient, big for us to see all these inputs, the digital inputs here, the analog inputs. All of this stuff is extra. It just makes it easy to begin programming with microcontrollers. If you look at my Elegoo board here, again, all this stuff is extra, and it's a nicety and makes it easy to start, especially if for beginners. But really, this Atmega 328 microcontroller is the brains behind it. We could take this off of this development board, plug it in a breadboard, and do all the same wiring and everything directly. There'd be a little more complexity that would have to get added, but essentially with this piece of kit right here, this microcontroller, the data sheet, and some some time and effort, you can do all the same things with this that you can do with with the development board. But this makes it a lot easier and incorporates other things, such as able to directly take power in, and we've got some other features, including just ease of accessibility and attaching the inputs through the development board. So a lot of the guide just also goes over how to set up the development board, how to assemble it. Talks about the Arduino IDE, which is the programming environment we're going to use today. And if you're not familiar with programming environments, an IDE is just an integrated development environment. It basically is everything you need to get started with programming, from writing the code via like the text editor incorporated into the IDE, to compiling and running your code, as well as debugging and everything. So it's got everything integrated into one, hence the name Integrated Development Environment. It's like a word processor for coding. So you don't need to use Microsoft Word to write something. Every computer, before you buy Word, comes with, Notepad or WordPad, these little tiny text editors. And you can accomplish a lot of stuff, basic stuff, with those. Well, the same is true for coding. You could write everything just via one of those text editors, Notepad, WordPad, or something like that. But just like you wouldn't necessarily want to write a term paper with WordPad or Notepad, you'd want to use something like MS Word. You wouldn't want to necessarily code with a text editor either. You'd rather use in an integrated development environment, just like Word would have spell check and things for grammar and a lot of other features for formatting and styling your text. An Arduino IDE or any integrated development environment will have a so-called spell check by being able to check for syntax errors in your coding, or they'll have auto-complete for certain common commands and keywords, as well as they'll have debugging and all kinds of different things. So the guide will go through that, but we're going to get right to the project. I've already wasted too much time talking about the guide, which you should just be reading in its entirety. So let's get started with your first circuit. So again, the first circuit is going to have 4 different parts, A, B, C, D, and A, B, C, D right there. And what is the first project going to do? Again, I'm going to go over a general overview. You should be reading this in its entirety, but Project 1, you're going to learn about light-emitting diodes, resistors, inputs, outputs, and sensors. And ultimately, we're going to create an RGB LED NightLight. So an RGB, again, stands for red, green, blue. It's like kind of a multicolored LED. And we're going to change the color using an input knob, and that's that potentiometer that I mentioned, that variable resistor. So the components that are going to be introduced in Project 1 are highlighted here: LEDs, resistors, which limit current flow, potentiometers, which are variable resistors that we control via a knob or something like that. So this little blue knob thing here is a potentiometer. And then photoresistors, which are a variable type resistor that is controlled via the light in the room. So circuit 1, blinking an LED. So that's all we're going to do in circuit 1. We're going to blink an LED. It is the hello world of microcontrollers. Again, it's the first program anyone really is typically going to do when they start off with Arduino. Not many components for this one. You just need an LED, a 330 ohm resistor, and 2 jumper wires, all included in that SparkFun Inventors Kit. And the components we're going to be using, again, we're going to be using a light emitting diodes. So these are just small lights made from diodes, hence the name, light emitting diodes. And we just say LEDs for short. And they have a positive and a negative leg. So if you look at this diagram here, the negative leg is shorter than the positive leg. Also, the negative side will have a flat edge on the bulb part of the LED, and just the bulbous part on the positive end. So the flat edge and the shorter leg indicate the negative side of the LED. And why do we care that we have a positive and a negative leg? Well, we care because that means that this component only lets electricity flow through it in one direction. It's polarized. And we'll talk about that just in a second, as you can see here, polarity. Also, an important thing to note when you're using an LED is you always use a resistor to limit the current when you are going to wire an LED into the circuit. The reason being is if you don't, the LED will just allow as much current as you're willing to throw through it, but it will destroy the LED. So it'll be really bright for an instant, and then it won't ever be bright again because you'll have burnt it. So we need a current limiting resistor in there. And this diagram shows these 5 single colored LEDs from white, red, green, yellow, and blue, all available in your kit. And this is that RGB LED. You'll notice it's got 4 legs as opposed to 2 that are in the other ones. That's because one leg is the ground, which each of these LEDs have a ground, the short leg, and they all have then one positive leg, whereas then this RGB LED has one long ground leg, which is counterintuitive considering we just said that they're shorter, and then 3 other legs for red, green, and blue respectively. But we'll talk about more when we get to that circuit. So I just mentioned resistors. Resistors resist the flow of electricity. They protect sensitive components like LEDs by just limiting that current. And the strength of the resistor is measured in ohms. So again, how much resistance to current flow this component, this particular resistor provides, is measured in ohms. So there's different amounts. So the concepts we're going to talk about are polarity, which is, as I said, when electricity is allowed to flow through an item in only one direction, like an LED. Hence why it has a negative and a positive leg, so we hook it up correctly in the way that we want electricity to flow. If you try to have the electricity flow through in the opposite direction, you will ruin the component and possibly the circuit as well. So resistors, however, do not have polarity, which means that electricity can flow through them in any direction. So throughout electronics, you're going to find out that there's a lot of components that have polarity, in which case you need to put them in your circuit with a little more care and effort, because electricity will only flow in one way. And then you're going to have things like resistors that don't have polarity, and you can plug them in either direction. Obviously a little more easier to deal with because you don't have to be as cautious. Ohm's law is also one of the concepts we're going to learn about in this circuit. And Ohm's law is just, as I've got it highlighted there, just is a relationship between the three fundamental elements of electricity, namely voltage, resistance, and current. So as you can see here, voltage is measured in volts, current, denoted by I, is measured in amps or amperes, and resistance is measured in ohms. And this equation is used to calculate what resistor values are suitable to sufficiently limit the current flowing through an LED. And so, although this is a concept that is very important in electronics, and obviously is going to come into play in this circuit, for all practical purposes, you can calculate what resistance value you need for the LED, because each LED will have a certain voltage drop across it, meaning it will take a certain amount of voltage, and microcontrollers are all capable of outputting a certain amount of current, and both that information will be known to us, what voltage the LED requires and the current that the microcontroller outputs. So we could calculate the resistance value, but to be honest, for all practical purposes, if you use a 330 ohm resistor, which was mentioned in this guide, in all your circuits with LEDs, you'll be fine. So you don't actually have to do these calculations, but it is important to understand how it works. I'll do a quick aside right now, actually. And just kind of go over in a little more detail what Ohm's law is. So as it showed there, just move that out of the way. Ohm's law is voltage equals current, denoted by I, times resistance. And as you can see from this formula, from this equation, that current and resistance are both directly proportional to voltage. And what I mean by that is if you increase either of these values, or both, you'll increase the voltage. And conversely, if you decrease current or decrease resistance, or both, you'll decrease the voltage. So they have a direct proportional relationship to each other. So again, increasing the current, you'll increase the voltage. Increasing the resistance, you'll increase the voltage. Increasing both, well, you really increase the voltage. And again, decreasing the same thing. And for all you math aficionados out there who are really good at rearranging formulas to figure out other things, if we want to find out the resistor value that we would need for our LED, we would simply isolate R, the variable that we want to solve for, by dividing both sides by, in this case, current. That'll cancel it out on this side, because again, anything divided by itself, as far as a fraction goes, is 1. And 1 times anything is just that thing. So this will give us resistance equals voltage divided by current. So this gives us a formula that if we wanted to find out the resistor value we need, we could look at the LED specs and find out what the voltage drop across the LED was, meaning how much voltage it uses, and what the current that the microcontroller provides. And we plug in those values and find out what resistor we need. However, for all practical purposes, we just know that a 330 ohm resistor will work great for what we need. But more importantly, what I wanted to show you here is you can see that there's an inverse relationship between resistance and current. So again, you can see that there's a direct proportional relationship between voltage and resistance, meaning if I increase voltage, which is in the numerator position of this equation, well, resistance is going to increase. And if I decrease voltage, which is again in the numerator position, decreasing a numerator of a fraction, will decrease the overall value. So resistance goes down. So they're directly proportional. But the opposite is true between current and resistance. They have an inverse proportional relationship, meaning if I increase the current, I'm going to decrease the resistance. And decreasing the current will increase the resistance. So whatever you do to one, the opposite effect will happen to the other. And if you're having trouble seeing this, think of it this way. If you have a fraction, like 1 over 1, pretend 1 volt and 1 amp of current, 1 over 1, that's equal to 1. Well, if I increase the denominator, so 1 over 2, we'll keep the voltage the same, so 1 over 2, I've increased the denominator, and as such, I've overall decreased the value. So I went from a value of 1 to a value of half, which is less. So again, increasing the denominator in a fraction decreases the overall value, meaning if I increase the current from 1 to 2, I decrease the overall fraction, therefore I've decreased the resistance. The same would be true if I had increased the current. So if I have a voltage of 1 and I increase the current, or decrease the current rather, instead of having 1, I have 1/2, which I can't divide fractions very well, so instead I'm going to follow the old rule. Instead of dividing by a fraction, multiply by its reciprocal. So 1 times 2 over 1, which is really just 1 times 2, equals 2. By decreasing the denominator, i.e. current, I've increased the overall value, in this case to 2, using these numbers. So again, whatever I do to current, the opposite is going to happen to resistance. And the same would be true if I had divided both, if I had taken this original equation, V equals I over R, and divided both sides by R. In order to solve for I would have current equals voltage divided by resistance, and the same inverse relationship holds true in both. So that's a little bit of a side tangent, which I apologize if you knew that already. But this is a very important thing in electronics. Ohm's law, in fact, it's the most important law, I would say. But it's really just here for kind of showing you the concept. It's not really coming to play too much as far as what you actually practically need to do to get your circuit going. And then again, this just talks more about the digital outputs associated with the circuit. Again, digital output has 2 states, on or off, higher, low, true or false. Just again showing the LED, that it's a polarized component, meaning it's got a negative side and a positive side. Negative side is denoted with a shorter lag and a flat edge, and resistors are non-polarized. And now this is showing you how you would hook up the circuit. So again, very simple circuit. You're just going to have a single LED put in the breadboard, and the negative lead of the LED with the shorter lag and the flat edge is going to get hooked to ground of your microcontroller, and the positive lead is going to get hooked up through a resistor, in this case a 330 ohm resistor. You can tell by the orange brown, which is the color coding system for a resistor. If you're not aware of the color coding system for a resistor, Google that, or the guide also does show you how to do that. Also, if you just want to look at your resistors in your kit and you're not sure how to figure it out, DigiKey has a really nice 4-band resistor color code calculator online. You can also click and get the 5-band and 6-band versions as well. But I believe all the resistors in the kit are 4-band. And basically just select the colors you have. If you have orange, brown, like in the kit we have here, it'll tell you the resistor value. As I was doing that, the resistor value was changing to 330 ohms. For example, if I had changed this to, it would be 370 ohms. So before, I'd encourage you to Google how resistor color coding works. But in the meantime, you can always go to something like DigiKey and just look at your resistor. And if your eyes are good enough, find out what the colors are and plug them into one of the calculators online. DigiKey has this nice one here, and it'll tell you the value. But the positive lead is ultimately connected to digital pin 13. It could be any of the digital pins, but we've chosen digital pin 13 in this example. So there you go. Also, another important note, this resistor really just needs to be in the circuit anywhere. So you could have just as well put this resistor on the negative lead going to ground, and then had the positive lead just connected directly from digital pin 13 to the positive lead. So again, as long as this resistor is in the circuit, it doesn't have to be necessarily in the positive lead. And then what you're going to do is you're going to actually go grab one of the examples from the SparkFun Inventors Kit guide. You're going to download that code off of their website, and you're going to be able just to upload all of the examples associated with this book. So you don't actually have to write the code yourself, but I would encourage you to do it just because it helps you understand how it's done. But just to get started, you can click into the examples, which we're going to be doing in a second. And ultimately, this first circuit of the first program is just going to let us turn on an LED by sending power 5 volts to the digital pin 13, waiting for 2 seconds or 2000 milliseconds, then turning off the LED by cutting the power to 0 volts to digital pin 13, waiting another 2 seconds, and repeat. And that's as simple as we're going to be, just blinking an LED. Again, it's the very first program most people do when they get started with Arduino. This is just a note that there's an onboard LED associated with digital pin 13, and almost any Arduino compatible board, like the RedBoard here, will have such a built-in LED connected digital pin 13. And this is kind of going through the code, but before we do that, we'll actually look at the actual code and not just the synapse here. I do apologize, this video has already went a little long, but it should go quicker from here on out with the other circuits because I won't have to go through that first part. So first and foremost, I'll show you the code actually. So I've also completed the coding challenges for these, so I'll be going a little bit beyond. Okay. I'm going to do a little bit of a sidetrack here and go to the when you download the code off of the SparkFun Inventors Kit website, you're told just to put that code in your examples folder associated with your Arduino IDE. However, I've done that. I've put that in the example code associated with my Arduino IDE, and it still doesn't grab it necessarily. So I'll show you what I mean by that. Typically, you're going to find your IDE by going to program files. You can Google how to get there, but I stored mine in program files. Then you can see Arduino IDE here. I'll make this a little bigger so you can see. Program files, Arduino IDE. Let me just, maybe too big. So I'll just start that again. You're going to go to your C drive, program files, likely, depending where you stored it, Arduino IDE, then resources, app, I believe it's library again, backend, resources, and examples. So it's quite convoluted to get there. You can Google this and how to get there. But these are the examples that automatically came. These ones here came pre-installed with the Arduino IDE, and you can see them here. If I'm actually in my Arduino IDE, I go to File, Examples, and I can see basics, digital, analog, communication, control. Same things are here: basics, digital, analog, communication, control. So this is where you're supposed to put your SparkFun Inventors Kit code that you download from their website, and as you can see, I did put all the SparkFun Inventors Kit code here. So the SICK circuit, so like this is circuit 1A blink, 1B potentiometer, 1C photoresistor, and 1D RGB NightLight. However, when you do that, you're supposed to be able just to click on the examples and have it show up and populate here for you to just go like this and grab. It doesn't seem to work for me, so what I do, and apparently this is a common problem when I Googled it, is just store it in that examples folder if you want, or store it somewhere else. It doesn't really matter, because ultimately you're just going to have to go there if it doesn't work for you, like it didn't for me, and double click on the actual INO file, the one that actually has the little icon like Arduino, and just pull up the program that way, and then just save it to whatever location you're storing your files in. So I'm going to X this because I already have it open, but that's something I've noticed there. And I just noticed I deleted my file explorer that I needed open. So I'll get that back up before we start here. I apologize for this. As I've said before, I am not a content creator. I'm not very good at this, but I'm doing this for the course just to put some stuff on the forum and help people through anything if they have questions. Do the code. Okay. Okay, so here's the actual code. I'm just going to make that bigger for a second. It's really simple. As you can see here, I'll just make that code a little bigger. So as you can see, all the SparkFun code starts off with the comment of just letting you know what the program does. In this case, turns on an LED connected to pin 13, on and off, repeats forever, and has links to the circuit diagram and where you can download the code. But in this code, it's pretty simple. You have in setup, you have your pinMode, which has pin 13 set up as an output. And again, they're using the magic number pin 13. I believe a lot of their code does this. I always prefer to be a little more explicit and have something like hashtag define, if I can spell that right, hashtag define, LED pin, 13, and use that directly. Use that directly in place. In this case, it added one more line of code, but it just makes it a little more explicit what this pin mode is for, like what I'm setting out as an output. Is it a push button? Is it an LED? Is it a motor? Whatever. This makes it very explicit. Oh, it's an LED pin. Set pin 13 to output. Whereas putting in the magic number 13 itself doesn't do much for us. But in this particular case, it doesn't really matter because so I'm just going to leave it unchanged because it is such a simple program. And then in loop, all we're doing is turning the LED high, so sending 5 volts to digital pin 13 by using the digitalWrite function, and then delaying for 2 seconds, so waiting 2 seconds while the LED is held high, and then writing to the LED, making it go low, so sending 0 volts to the LED pin, digital pin 13, and then waiting another 2 seconds. And again, I say 2 seconds, obviously you see 2000 here. Again, the delay function takes in milliseconds, a number representing the milliseconds as a parameter. So 2000 milliseconds is 2 seconds because 1000 milliseconds is what is in a second. So again, pinMode is the function. Just to go over this again, every Arduino program is going to have 2 functions for sure. That's setup and loop. Setup just runs once, and again, you typically use it to set up your pins as inputs or outputs, or do anything that's that you only expect to happen once in the code to initialize anything, any libraries you're using, like if you're using an LCD or an IR receiver or something like that. You're going to set it up once. In setup only runs once and then never runs again. Whereas loop runs continually for the length of the program, so it'll just keep running until you shut off the Arduino or there's an issue. And so those 2 functions always happen. pinMode function is, as you can see here, it simply takes in 2 arguments. The first one being the pin number, the number associated with one of the outputs, one of the 14 digital outputs or the 6 analog outputs. And then you can write the keyword output or input, all caps, indicating what this is. An LED is always an output, but for example, if this was like a potentiometer, it would be an input, or a push button would be an input. And then in loop, The digitalWrite function also takes in two parameters, and again, it takes in as its first parameter the pin number of what what your sensor actuators is attached to, and you then give the keyword high or low, indicating whether you want to send 5 volts to it, which would be high, or 0 volts to it, low. So again, there's only two states for digital: high or low, true, false, 0, 1, that sort of thing. And then delay is simply a function that pauses execution of the program. And we'll talk about that further as we go down in further videos, but this actually stops execution of the program for 2 seconds, which there's some things associated with that as we go further. But for this simple example, this is going to be great. So let's actually see that work, because this video is getting quite lengthy. So we're going to plug in, and you'll notice there's a lot of extra stuff. I've got kind of all of the 4 circuits hooked up all at once, so I'll zone in and tell you exactly what to focus on as we get this going. So I hooked it up. I'm just going to see it's on pin 16. Go to port pin 16, make sure the board is selected, and we're going to upload that code. I could have also alternatively just compiled the code first, verified it was good to go, and then uploaded, but this is such a simple code I can tell that it's good to go, so I made the leap of faith and went straight to uploading. And there's nothing to the serial monitor in this case because it's such a simple code. All this code should be doing is, let's take a look, having an LED blink on and off. That's all this code does. So I've got a lot of other circuitry hooked up here that's not necessary, but again, you can look at the examples online to see their stuff. But really, the only thing associated with this is I have this red LED here. The negative end of it, if you can tell, goes through, the negative lead is hooked up through this resistor, which goes to the ground on this breadboard, which I hook into the ground of the microcontroller. And the positive lead is going through this orange wire here, which goes to digital pin 13. So again, the negative lead, the shorter lead with the flat side of the Arduino, goes through a resistor, which ultimately gets connected to ground, and this breadboard's ground is connected to the microcontroller's ground. And the positive lead goes through that orange wire that is connected to digital pin 13. So again, I understand that all this circuitry does kind of make it harder to see the easy part of the circuit, but that's only part of what this video is for, so I wanted to just show all the circuitry. But again, if you're looking for the simple circuit associated with that, let's see if I click the right thing. Blinking LED. And you can see there's a little more detail in when you go online compared to the guide. So just keep that in mind if you want the full details. But yeah, the simple circuit would be just like this, kind of what we showed in the guide. Simple LED, one end connected to ground, the short leg, the negative leg connected to ground, the positive lead connected to digital pin 13, and the resistor shown here is on the positive lead, but again, it could have just as well been on the negative lead. It doesn't matter. This is a schematic here, the pinout. Lots more detail can be found on the website. So that's not so much the point of this video. I'm just going to show some coding challenges. So in this particular case, I have all this stuff connected, but just to show you that this is what you'll get, just a flashing LED blinking at that speed with this first example. Now I'm going to go to coding challenge. There's a coding challenge associated with this. I guess I'm jumping ahead of myself and should just kind of got a mess going on here. Let me just fix this. Okay. So I do apologize for the video again, not a content creator. So here's the main things to note about the code. Setup and loop, as I said, void setup, they're both void functions, meaning they don't return any values, and neither of them take parameters. And both these functions are in every single Arduino program. Setup runs once, loop runs over and over again. Input or output. So before you use digital pins, you need to tell the RedBoard or your Arduino board, whatever you're using, whether the pin is going to be used for input or output. And in this case, I've said digital pin 13 is for output because it's an LED. I need to send voltage to the LED to light it up, and I need to not send voltage to it to have it not lit, but I'm not receiving any data from it. So an LED is what's called an actuator. It's something that's like causing an effect in the environment, like a motor or an LED or something like that. So that actually does something to the environment, so to speak. So it's set up as an output, whereas if it was a sensor, something reading data from the environment, like a potentiometer, which is, I'd be controlling it, but it'd be reading that data, or a photoresistor reading the ambient light level, or an ultrasonic sensor reading data, based on distance. If it like a temperature sensor, anything like that, any sort of sensor, you would typically set up as an input. Throughout this guide too, I've kind of used color coding sometimes to indicate certain things. So inputs are often denoted in pink, and output is often denoted in blue. No particular reason for that, just in Microsoft Edge, the browser I use a lot of times when opening PDFs, there's only like 5 colors that you can highlight things in, so that just happened to be that. Some other code to note here is digital output. I used digitalWrite to because I was using the pin as an output, I needed to be able to digitally write to it or not. If I wrote high, which I did when I was turning the LED on, it output 5 volts to the LED. Low, output 0 volts, so turn the LED off. The delay function again causes the program to wait for the amount of time that you give it as the parameter. In this case, showing as 2000. 2000 represents milliseconds because that's what the function expects, a parameter in int, which represents milliseconds, and 2000 milliseconds equals 2 seconds. Again, comments. I mentioned that at the start of the program, there were a lot of comments by SparkFun, and particularly multi-line comments, which have this /* style. So basically, 2 types of comments. You can have single-line comments, which you just have a double //, and you can only, whatever is follows that, as long as it's on the same line, is going to be commented out. Basically, the compiler is going to ignore it, knowing it's not part of the program, but really it's just something meant for the programmer to read and understand. Or you could do multi-line comments where you just start with a /*, and end with the */, and that'll let you to have comments over multiple lines. So again, a single line comment would be something like this, single line comment. But if I just went down here and wrote something else, that's going to give a compiler error. If I try to compile that, the computer's going to get all upset because saying I have no idea what this is. See, like it's giving you some error and be like, error FDGD does not have a type. It's expecting to be some type of variable, but if I commented that out, I would be fine. But all that's just to say that anything after the double / on the same line will be commented out, ignored by the compiler as far as the programming goes, but you can't go multi-line. Whereas if, again, multi-line, I could write gibberish on all kinds of lines, and you see it's all grayed out, and then I just have to end it with this. Can't type today. So again, this video is quite long. Again, I do apologize. If you're still watching, good on you. And then there's the coding challenge associated with this. It basically says try adding and changing the delay values and adding more digitalWrite commands to make your program blink a message in Morse code. So that's what I did. So I'm going to show you that right now. So this is coding challenge 1. Morse code. So first I'm going to pull it up, and then we'll actually upload it onto the microcontroller and just see how it works, and then we'll talk about the code. And then that might be the end for this video, because this video is going quite long. So I'm just going to upload this to my microcontroller. It's already set up. I'm going to just directly upload it, and then while that's waiting to upload, we'll see what happens down here. So I'm not sure how well that shows up there, but it's, in case it doesn't, it says enter message, well, enter MSG colon, because this is an LCD screen which only allows 16 columns or 16 characters and 2 rows. This LCD screen isn't part of the first project at all. I'm just using it as kind of an extra feature, but it will be incorporated as you go along. So enter message here. You're just going to go to, I'm going to open up 2 things at once. So you're going to open up your serial monitor on your Arduino IDE, and this serial monitor basically allows you to communicate. This is how you communicate via the computer and your Arduino if it's hooked in via USB, which mine is, as you can see here. So I'm going to type something and enter a message. I'm going to write my name. Actually, I'm just going to write hello and press enter to send it. And you can see hello is showing up on the screen there. I'm just going to restart. I'm going to press the restart in the Arduino IDE just so I can do this again so you can see hello. I'm going to type hello in again, and it's not going to actually send to the Arduino until I press enter, so I'm just going to make this big first so you guys can see it, and then I'm just going to press the enter key, and you'll see the message I typed in, hello, show up here. I'm going to press it and get right to this. So I just sent the message hello, and you can see sending hello, and then it's dot, 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 dot. And you can see it's saying dot or dash, there was the first dash, on the LCD in sync with the LED flashing. And there's a delay between the dot and the dashes, and I'll show you that, and then it just shows I wrote hello to the screen. That LCD screen's not really showing up very well, so I'm not sure how much you're actually seeing. But we'll look at the code and then see what's going on. Before that, though, I'm just going to adjust something here, which I'll explain in a second what that is. Let's try this. Oh, I apologize. Not sure if that's any better. But I'm going to explain the code, and hopefully we'll be able to see what's happening. Okay, so for the first coding challenge, which was to create Morse code essentially, a couple things I did. One, I had to go to Wikipedia and find out Morse code. But you can read this on your own. You know, Morse code used in militaries across the world. It's a way to communicate using dots and dashes, and like telegraph machines, that sort of thing. You've probably seen it in movies and TV show if you're not familiar. But basically, this is Morse code here. The length of a dot is 1 unit, and a dash is 3 units, which is just the length of how long you press or hold something down. So like 1 unit would be a dot, and a dash would be hold it down for longer. And this is A through Z. I didn't incorporate numbers in this code, although it would be very easy to do. But A through Z, and just shows how the dashes are. You have like a dot dash for A, dash dot 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 for B. You can see that hello is 4 dots, and then 1 dot for E. The L's are a dot, a dash, a dot dot, and then O is 3 dashes. So, not sure if you'll be able to remember that, but I did put that up here. in my comment using a multi-line comment. This extra asterisk is a way to do a multi-line comment and have it recognized by some programs like Doxygen or something, which just allow you to create really nice HTML documentation from your Arduino project automatically, so it can get automatically generated. That's beyond the scope of this video, but that's why there's that extra asterisk there. But basically this comment, which isn't really good because it doesn't explain me or what the program does, but I just said if the user types in the word hello, the following Morse code message will display. 4 dots representing an H, 1 dot representing an E, a dot, dash, dot, dot representing an L, that repeats twice, and then 3 dashes representing an L. So I'll go through the code here and then we'll be done this video, I promise. But there is a fair bit of code. A lot of it's not necessarily needed for the coding challenge because I added extra things like an LCD screen, which I'll explain what was necessary to do the coding challenge and what wasn't. So first of all, I've added a couple one library here. So if you want to add a library, basically code that someone else has written, whether that's like which you can find on GitHub or just scour the internet, or go over to your trusty IDE and click on the library thing and search for a library in here, like Liquid Crystal. If I wanted that, you'll get it here. Now I obviously have it already installed, so I'm not going to do that. But libraries, again, are just a collection of code that someone else has written and that are often take away a lot of the complexity of doing certain things with microcontrollers and all the various components, actuators and sensors. So Liquid Crystal is a particular library that's used for non-I2C LCDs. And I2C is a communication protocol, again, beyond the scope of this project, but this library is what you need to install if you want to use the LCD screen that I'm using. And then I've just used hashtag define. This is just a way to create a constant, basically a named variable that doesn't change. So in this case, VO pin for contrast level. This is again associated with the LED. One of the pins on the LED can be adjusted via a potentiometer to affect the contrast, how the text appears versus the background. And this is often normally controlled with a potentiometer, but I only had 1 or 2 potentiometers come in the kit and just didn't have any extra, so I just or I have it actually, I do actually have the potentiometer on the board, but it's being used for something else and I didn't want to repin it. So I'm just I'm using software to control the contrast. That's all that does. Pin definitions. I've created constants, which I could have used hashtag define. Using hashtag define and doing this are one in the, like, they create the same effect. It's just this is hashtag define is kind of an older style to do it, a C style, programming language C, which Arduino is based off of C and C++. And using this style where you go const int, which creates an integer variable that's constant, that can't change, which is doing the same thing as this define, is more or less the new C++ style. So I just included both just so you could see the differences. Basically the main difference is here you don't use an equal sign, or an assignment operator, which is this thing, and you don't have a semicolon afterwards, which you do in these. But these constants, ints, just represent the various pins associated with an LCD. The register select pin, the enable pin, and the data transfer pins. I use 4. There's 8 on the LCD, but we only need 4 of them. And yeah, I've just given names to the actual numbers. So that way down here, when I set up my create an instance of Liquid Crystal of this LCD, I can actually just pass in the names, RS, EN, the data pins. So it's explicit what parameters are going into the parameterized constructor to make this instance of LCD screen. I could have just as well put the pin numbers themselves, 7, 8, 9, 10, 11, 12, without having done this line of code. This just makes it a little more explicit. It's considered better programming style. I also created a constant for the VO pin, which is pin 6, and the VO pin is again is that pin that's used to control the LCD contrast, which is what this value is associated with it. This is the value I'm sending to that VO pin. 100. So that I could send it a value from 0 to 255. That's the resolution I could give it. I chose the value right in the middle at 127 when I started. I just changed it to 100 because it wasn't showing up very good on the computer. But that's that. And then I've created a constant for the LED pin, which is pin 13. You'll notice I have this all capitalized, by the way. By convention, it's not required, but it's convention to make constants uppercase and have the letters, make it all uppercase letters and have words separated by spaces. But, and that's what I did with hashtag define. And although that's good convention, I find that in a lot of the tutorials, including SparkFun on their website and a lot of stuff online, they don't really do it when they're using const int, which to me makes no sense. I actually like it. Because again, having everything uppercase indicates to me, oh, that's a constant, as opposed to a variable. Because if I see LED pin later on in the code, I have no way to know, is that a variable? Can I change that in code, or is that a constant? Nothing about this lets me know. So I actually like the all uppercase thing, but I just kind of am going with what I see on a lot of tutorials, so I've done it this way. But you choose to do it however you want. Again, they're convention, it's not a hard, fast rule. It just makes your code more universally understood. And then these are the timing constants. So these are what I'm using I'm using these variables that I'm creating more constants of type int, but the variable names are dot duration, dash duration, symbol pause, letter pause, word pause. These are all just ultimately the ints that I'm going to use to control the delays in the code. So these just represent the milliseconds that I wish to delay. So after a dot, the duration that I want a dot to flash for, like that I want the LED lit, is 250 milliseconds. A dash, I want that for 3 times that amount. And why 3 times that amount? Well, because according to Morse code, the length of a dot is 1 unit and a dash is 3 units. So that's where I came up with that. A dot duration, the symbol pause between the symbols, is the same as the dot duration. So I could have just put 250 here, but because I already declared dot duration to be 250 milliseconds, I'm just using it here. A letter pause is the same as a dash duration. I put dot duration times 3. Again, I could have put dash duration here, considering I already declared dot duration times 3 as dash duration. It's all just a matter of what I think is explicit and what's better understood. Word pause is dot duration times 7. So I have a longer pause between words. In this case, in the example I gave with hello, I had a single word, so this didn't come into play. But if I would have had hello world, there would have been a longer duration between the O of hello and the W of world. This is the Morse code dictionary. I just have a link to the Wikipedia page that I just showed you. But this is basically creating a one-dimensional array of type char pointer. So pointing, and again, it's constant. I don't want people changing this. And all of these values in this one-dimensional array all just represent, A, B, C, D, E, F, G, H. So that's the H, the 4 dots. This was the E, the single dot here. And yeah. You could be more explicit with this. I've created this one-dimensional array of char pointers, which are just like C-style strings for anyone familiar. I created here where you can't really tell, what's A without counting through the alphabet. Like I know this is Z and I know this is A, but I don't know what this is right away without I'd have to count. Right? I'd have to go, okay, F, G, H, I, J, and figure out. You could have been more explicit and create like constants for each of them. So you could have done a char and made a constant, or you could have done a constant char pointer, so C-style string, for A, and set it to, dash, and set it to that, and done that for, the entire alphabet, and you would have taken more room up in the code initially, but it might have been a little more explicit. There's various ways that you could have done this. I did it this way because I didn't really need to see what A, B, and C is because the coding kind of takes care of it for me. But you could have done that. Then these are my function prototypes. So I've created these 3 functions. Blink Morse code that takes in as a parameter a char, And then I have blink dot and blink dash. These are all void functions, so they don't return any values. And these are just function prototypes. Again, it's just me telling the compiler, hey, these functions exist in the code, so be ready. Not as required in Arduino, but definitely required in C++. If you order matters a lot in C++, so if I don't have these function prototypes, if I call the function before the function is defined, I'll get an error. So a lot of times you use function prototypes so that you can have all your functions after setup and loop and still be able to use them. Then I have my setup function here, which basically sets up my pin modes. So I basically declare my LED pin and my VO pin is output. So again, VO pin is that one that I'm sending an output to, a value from 0 to 255, controlling the contrast of my LCD screen. And then here's where I'm actually doing that. I'm using analog-write, which is a function that we won't necessarily talk about in Project 1, but digitalWrite can send two values, either high or low, to a digital pin. Certain digital pins are pulse width modulation pins. They accept values from 0 to 255, which we'll talk about later, but that's essentially what this is. So VO is just like digitalWrite, takes in two arguments, the first one being the pin you want to write to, and then the second one being high or low. Well, with analog-write, you're sending a value between 0 and 255, and the value I happen to be sending is right now this 100 value. Just representing how I want to control the LCD contrast level via software instead of using potentiometer. And then both these lines of code are associated with the LCD. So just like you go serial.begin if you're using the serial monitor with Arduino, you go lcd.begin if you want to use an LCD screen using the library. And you have to pass in these two parameters, 16 and 2. This represents the number of columns for the LCD I'm using, which it's got 16 columns or 16 characters across, and it's got 2 rows. And then in this case, I'm just printing lcd.print. I'm printing the string enter message to the LCD screen, as you can maybe or maybe not see there on the LCD screen, depending on the contrast. And then I also am calling serial.begin, passing in the baud rate of 9600, and I'm calling that just so I can also see things on the serial monitor if I want as well. So, and you'll notice I have this multi-line comment again before setup and before loop and a couple things, and it's got this syntax again of the /**, and ends with a /**. Again, if it didn't have this double asterisk, it would simply be a multi-line comment, meaning I could just comment over several lines without doing that // on front of each line. But by adding this extra asterisk, and you can see the color changed on that at brief. Let me do it again. See, it's all gray, and then here it changes. This is a special way of telling the compiler, hey, I want you to, this is a special comment that then I can use later in a program like Doxygen to generate nice HTML documentation for this program. So, and then, again, it's beyond the scope of this program, but if you're interested, just look up Doxygen, DOXYGEN, and it'll explain why I have this at brief and at file. Oh, I didn't put it up here. Typically, I would have at file, the name of this file, at author. I could put my name, lots of different things, which I guess I neglected here, but it's just little tags to let me know. In this case, at brief just says this is the brief description of the function. I could have an at detail and have a detailed description, and it just affects how it's formatted on a web page, essentially, that gets generated automatically. And this is the loop that runs continuously. So all I did here was basically set up my two pins, my LED pin and my contrast pin, as output, and control the contrast of my LCD screen. In the loop, I'm going to go if serial.available is greater than 0, and what that does is that basically says, hey, if someone's typed something in the serial monitor here, if there's something that someone's typed and then pressed enter, if I've sent something to the via the serial monitor, it's going to be, okay, hey, there's something to read, and we're going to come in here. we're going to come in this code. If otherwise, I wouldn't come in here. So if someone did type something in through the serial monitor, I'm going to come into this code and I'm going to go serial.read string until next line, meaning I can write up a bunch of stuff here. Hello world, what's going on? Question mark. And there's not a next line. As soon as I press enter, that tells the computer that's like a next line symbol. That's that \n. So I'm going to read a string until the next line character, and I'm going to store that string. I'm going to store that, whatever I typed in, into a string variable called message. And string variable is kind of very specific to Arduino. In C++ and in C and different languages, sometimes there's strings or a data type, sometimes there's not. Not really in C. There's C-style strings, those char arrays, but you don't actually have a string data type per se. But you do in Arduino, so that's kind of a cool thing. So whatever I type in, we're basically going to store it in this variable message. And then I'm calling the trim function, which just basically takes any white space. So if I had accidentally typed the space bar a bunch of times before typing the message, and then maybe at the end, that won't be included in my code. I'll trim that so that message, when it's used further on in the code, doesn't have that white space. And then this is all associated with the LCD screen itself. I'm going lcd.clear. Basically, if there's anything already in the screen, I'm just clearing it. I'm setting the cursor to 0, 0. That puts it at row 0, column 0. And then I'm printing sending. And then I'm going to column 0, row 1. So the first parameter is actually the column. So whether it's left or right on the LCD screen. And then this is, there's only 2 rows, 0 and 1. So this is the top row. 1 would be the bottom row. So I'm writing the keyword sending on the top left of the LCD screen, and then I'm writing the message, whatever I typed in, on the bottom left, or the bottom of the bottom row. And then I'm delaying 2 seconds, just so that the user can read whatever it is that that they've typed in. And then I'm clearing the LCD screen. Let's just look at that first. I'll just send hello world. I'm going to click it really quick, and then we'll get to and we'll make this big here. So I enter the message, sending hello world. You might have seen it there again. It's really hard to tell on this screen if you're seeing it. So I'm going to do that again and really hope that you can see it. Hello Dan this time. Let's just do it for fun. So it says sending hello Dan, or hello can, or whatever I typed in. So that's what that's doing. And yeah, and then I clear the LCD screen. And then here's where I'm going to actually start translating and sending Morse code. So translate and send Morse code. I'm going to use a for loop, which again is a little beyond the scope of just the circuit 1A, but again, this is the coding challenge, so I went with it. And I'm using a for loop to iterate from 0 up to whatever the message length was. So hello world would have a message length of 11, because HELLO, that's a length of 5, space, which counts as a length, so 6, world. So now let's count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it has a length of 11. So again, I'm going to use a for loop to go from 0 up to, but not including 11. So this, in this case for hello world, this wouldn't go on 11, but it would work on 10. So this is going to iterate 10 times. And every time I go through the for loop, I'm going to increment I++. So that's how for loop works. This is your initial value you give to the variable. This is the condition you check each loop, and this is your update, what you do. So basically I'm going to come into the for loop, and I'm going to take message sub I, which is message sub I is basically treating the string as a char array, because strings are in fact just arrays of characters. So I'm grabbing the first letter in the string. That's how this works. So the first letter in the string hello world would be H. So I'm grabbing the H, and I'm going to put it to uppercase. This to upper is just a method that takes everything and puts it to uppercase if it can be put to uppercase. So if it's already in uppercase as a letter, it won't do anything to it. But if it's lowercase, it puts, and this just allows us to have, it just allows for the coding to be easier if I have everything either in uppercase or lowercase. So I could put 2 lower and put everything in lowercase. The 2 uppercase doesn't really matter. It's just so that everything is in, it's just so I don't have to check a character if it's uppercase or lowercase. It just allows for ease. So I'm storing the H that I'm putting to uppercase as in a variable C, which is a char variable, which is what H is. Each of these values in a string are a char. And then I'm going to go if C equals empty space. So if the char that I read is an empty space, which it will be between the W and the O of hello world, but nowhere else, if it's an empty space, I'm going to call the delay function with word pause as the argument to the function. Remember, delay expects an integer representing the number of milliseconds you want to delay for, and word pause is a constant I created earlier to delay for dot duration times 7, and dot duration is 250 milliseconds, so 7 times 250 milliseconds, which is going to be 1.75 seconds. And that's only going to happen between words. So when char is an empty space, which is only going to happen between words, presumably. That's what I'm going to delay. Else, meaning if char is not an empty space, else if char is greater than or equal to capital A and the C, the variable of type char, is less than or equal to uppercase C, then I'm going to do something else. And what this line of code does, this verifies if char is in the alphabet. So I didn't really incorporate numbers in this code, so I'm not expecting the user to type in 0 to 9 or any special symbols. Again, I could expand this code later and do that, but in this particular case, I'm just checking to see if the character they typed is it's in the alphabet. And the fact that I'm using uppercase A and uppercase Z here, that's because I took whatever they typed in and I put it to uppercase. If I put it to lowercase, I would be checking this with a lowercase a and a lowercase c. And if I didn't want to put it to uppercase and I just wanted to make life harder on myself, I would have just read in the message as is without going too upper or too lower, and I would have just read it in whatever case the user typed it in. So for example, if I typed in hello world with a capital H and a capital W, the H and the W would be uppercase letters and all the other cases would be lower. I'd have to add code I'd have to complicate the code by doing something like, I'd have to be like, if C is greater than or equal to uppercase A and that, or, and do this whole line of code again, but check it with lowercase letters, I would have to do something like this, which just is unnecessary. Like this is just adding complexity to the code when I could just right away take whatever they give me and put it to uppercase, to lowercase, doesn't matter, and then just check with those limits. And why this works is because char is actually like an int. It's just, behind the scenes, it's really just an int. So when I'm going, is C greater than or equal to uppercase A? Well, C is the char they typed in, and it's really just, and the letters of the alphabet, as well as numbers and stuff too, are all ints under the hood based on something called ASCII code. And I'm not going to go into that in the video, but needless to say, uppercase A is actually something like, 97. Oh, actually, what am I talking about? It's 65. Lowercase a is 97. Uppercase A, its value is actually 65. So it's the int 65, or the hexadecimal value 41. But it has an int value of 65, where Z has an int value of 26 past 65, I guess, 90. So what I'm really saying is C, whatever they typed in, if they typed it in A, which it doesn't matter if they typed in lowercase or uppercase A, I'm putting it to uppercase. And so I'm saying, hey, is the thing they typed in, let's say it's an A, is A, which we know is 65 under the hood, is 65 greater than or equal to 65? Yeah, okay, well, it's a letter then. Or if it was Z, is it 90? So basically, if the char can be interpreted as an integer between 65 and 90, that means someone typed in a letter. And what am I going to do? Well, then I'm going to call the blink Morse char function passing in C. And I'm going to delay by letter pause, which again is just a variable I've created, meaning I'm going to delay in this particular case by, 750 milliseconds, 3/4 of a second. Where am I here? And so that's what that's doing. I'm going to jump down to blink Morse code, and I'll come back to this, but blink Morse code is the thing we are actually calling, the function we called here. So let's go see what that function does. So blink Morse code here, again, these are just Doxygen style comments, special comments. This just says that the parameter that this function takes in, C, is the character to encode in Morse code. And this function is what's actually responsible for blinking the Morse code for a given character. So void blink Morse code takes in a parameter of type char, so it takes in an argument rather of type char, and this line of code is going to access the Morse code array index associated with that character. So again, that Morse code array is this array here, which contains a comma separated list of values associated with the alphabet in Morse code. So this is A, B, all the way down to Z. So where am I? So yeah, so I'm gonna access the index of the Morse code array by going C, the char that got passed in, C minus uppercase A. And so what this does, say if C is an A, say if the first letter is actually an A, well, it's going to go A minus A, which is, under the hood, 65 minus 65, it's going to become 0. And I'm going to access the value stored at Morse code array 0. So do you see how that works? If I typed in an A minus A is 0, and I'm going to access the value stored at Morse code array index 0, which is going to be the Morse code value associated with A. And if I was to lost my spot again. If what was typed in was a C, so if the char that got passed into the blink Morse char function was a Z, well, Z minus A is going to be under the hood 90 minus 65, which is going to be 25, and I'm going to go to the index number 25. Well, what am I going to find at index number 25? Well, index number 25 is the last thing in the index, because there's 26 letters in the alphabet, so therefore there's 26 little elements in this array, and they're numbered from 0 to 25. So the 25th index is Z. So that's how that works, just in case it wasn't clear. It probably isn't anymore after me talking, but that's what's happening here. So I'm basically accessing the index associated with the character. I'm accessing the index of the Morse code array that we created based on the character that got passed into this function. And then I store that code from the array into this variable code, which is a variable of type char pointer. And it's constant for the purposes of this part. Really don't need a constant, but that's fine. And then I'm using a for loop to iterate from 0 up to code sub I, which will be, again, code. What I passed it was a string. In the case of H, it'd be the string dot dot dot. In the case of L, it's the string dot dash dot dot. But code is really just a string, a C-style string, which is a pointer to a char. But so when I go code sub I, I'm accessing the individual letters or the symbols of that string. So for H, or let's use L, I believe, is dot dash dot dot. So this string here. So code sub I, well, when I is 0, I'm going to access the 0 index of this string. And then when I is 1, I'm going to access this. When I is 2, I'm going to access this one. And when I is 3, I'm going to access this one. So 0, I'm accessing that. 1, I'm accessing that. 2, I'm accessing that. And 3, I'm accessing that. So basically, I'm going to go through the entire string, which represents the Morse code, and I'm going to compare the value and see if it's equal to null. equal to the special character \0, which indicates that I'm at the end of the string. So even though it doesn't show here, whenever you get to the end of the string, there's this, symbol which represents a single character, just indicating the string is over. So it's not shown when we write the string, but it's technically when I got to the end of the string, boom, I would have hit this special character. So I'm basically going through the string, iterating through this C-style string, and as soon as the value, as I'm iterating through the string, equals this null character, the special character, \0, the condition is going to be, as soon as I equal that, this condition is no longer going to be true, because this condition says as long as I'm not equal to that, I'm going to keep going. Then I'm going to jump out of the code. So while that's not true, meaning while I don't get to this last character, while I have still characters to read in the string, I'm going to go if code sub I equals a dot. So if it's equal to a dot, that's this double equal sign, indicates if it's equal to a dot, I'm going to call the blink dot function, which is a function I've created. Else, if code sub I equals a dash, I'm going to call the blink dash function. And then finally, at the end of this, I'm going to delay for the symbol pause. So I'm going to delay the amount of delay I've decided that I should have between the different symbols. So, a dot and a dash or a symbol. And so when I say blink dot versus blink dash, well, what does that do? Each of those functions are, essentially the same thing, but blink dot, again, it's a function that takes no parameters and returns nothing. And it simply turns the LED high. I'm going to ignore this for a second, the LCD stuff. But really what it's doing is it's calling digitalWrite, turning LED pin high for a certain amount of time, dot duration, which again was 250 milliseconds based off this constant I created. And so it's going to turn the LED high for that amount of time, and then it's going to turn the LED low. This is some other stuff I had for some reason. And then I delay for symbol pause, so the right amount of time between the symbols, between dots and dashes that I've decided on. So pause briefly to separate elements of the same letter. And then I call the clear, then I clear the dot text briefly before the next symbol. This is just kind of something I'm doing with the LCD. Instead of, I just didn't want to have dot remain on the screen, even if I have like 3 dots in a row. I didn't want dot just to stay up the whole time. I wanted dot to show up and then disappear on the LCD screen, show up again, disappear. And without this code, basically dot just stayed on the screen the whole time if there was consecutive dots, or similarly dash stayed on the screen if there was consecutive dots, and so this code just prevents that. But this is LCD stuff, so I won't focus too much on it. But basically, if you are concerned about the LCD, I set the cursor to 0, 0, the top left corner, 0 column, 0 row, and then I print dot. And all this extra space just basically fills up the 16 characters, because again, the LCD screen has 16 characters across, and I just write dot and erase anything that else was on there by using empty spaces. I could have called dot and then called clear, but this is just easier. And then down here, I set the LCD cursor back to 0, and I overwrite all the spaces. So this just is 16 spaces or whatever that overwrites dot. So that way, again, if I have consecutive dots in a row, I want the word to actually disappear for a brief second from the LCD screen before reappearing. And again, I just pause for the symbol. The blink dash function works almost identical to the dot, just with, I'm outputting the word dash on the LCD screen, but otherwise I'm writing the LED pin high, but I'm having the delay longer because it's the dash duration, which I believe is 3 times longer again that I made. So dot duration times 3 is the dash duration, and again, that's all based off of the Wikipedia page that says the length of a dot is 1 unit, the dash is 3 units. So blink dash, so yeah, so I just delay a little longer, but really I'm still turning on the LED for a certain amount of time and shutting off, the same as the blink. The only difference is the duration, and I'm writing dash to the screen instead of dot. And again, same thing, this just clears the dot text briefly before the next symbol. And then finally, this is some scrolling text. this length. This is already pretty long as it is, so if you're interested, just pause the video and read what's happening here. But this just displays scrolling text. So after I write, I'll briefly mention it here. After I do the individual dots and dashes for the thing that you've typed in, the message, hello, I'll just have hello, or whatever the message was, scroll across the screen from right to left, scrolling off the screen, writing the letter, the alphabet letter associated with what you typed in, and in parenthesis, the symbol, the Morse code symbol. And that just scrolls off the screen. And that's what all this code accomplishes, essentially. So you can read that for more details if you like. Yeah. So that's all the code do that. It's pretty convoluted, but again, ultimately what it's doing is accomplishing this. I apologize, I know this video is an hour and a half, and no one's likely to listen to it. But here's what it does again. So I'm going to enter a message. So I'm going to write hello world. I'm going to type hello world on the screen. As you can see over here in my serial monitor, this is my access to the computer. So when I type something in here, as soon as I press enter, that's going to send the message to this to the Arduino. So I'm going to press it. It's sending hello world dot 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 dot. So 4 dots, another dot, dot, dash. So I'll restart this and just, I want you to focus on the right here, hello. Up here it shows 4 dots, H, 1 dot for E, and this. So if you follow this, you'll be able to see what's happening. Because again, even though there was 5 dashes that happened kind of right in a row, you'll notice after 4 of the dashes, there was a little bit of a lull, a little bit of a longer delay, and then a single dash, a little bit of a delay, and then another dash. So technically, this program starts off with 6 dashes in a row, but 4 of them are associated with the H, and only 1 is associated with the E, and then this. So let's do that again and see if that works out any better. So just try to follow along so you can tell the difference there. I'm just gonna restart that. So I'm typing in hello world into the console, pressing enter. So I sent hello world to the LCD, dot, 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 and dot, that's associated with the H. Then there's a pause, dot, that's associated with the E, pause, and then this dot, dash, dot, dot is associated with the L. And then the next L, same thing. And then there'll be a longer space, and then 3 dashes for the L. Oh, and then world, of course, which my example doesn't show, but we could find out what it is. CYXW, so world would have been that. And then hello world, showing each letter with its corresponding Morse code, scrolling across the screen. Again, it doesn't really look good on the computer here, but and you can play around with the delays and the flashing of the LCD to get things looking how you want. I'm going to quickly show you, well, the video is long enough anyway already. Let's quickly save this and go save as Morse code. We're going to save it as we're just going to save it here as Morse code, blinking LED, no LCD. No LCD. So I'm going to show you the code, how it's not as complicated as I have it here, because this code is incorporating this LCD. But if you just want to see the blinking LED, which is really all the code challenge required, I'm going to take away the LCD so we can do that. And I'll take away this comment. We'll just really simplify the code. So I don't need this contrast, this constant, which is associated with the LCD contrast. I don't need the library. I don't need this comment. Actually, I will leave the comment just so you can see. I don't need a multi-line comment. Let's just keep the comment simple to a single line. I don't need these pin definitions. All this is associated with the LCD, so I don't need that. I'll even take it away, make it simpler. I won't even have this constant for the LED pin 13 because we can just plug that directly into the pin mode. I don't need this. I do need the constants. I'll keep those for now. I need the Morse code. I don't need LED pin. I'm just going to put pin 13 hard-coded indirectly. Not necessarily good coding, but this is associated with the LCD screen. Don't need this. Don't need this. Use that. Don't need these oxygen comments. Let's just really simplify it out. Technically don't need these function parameters, function prototypes, so we'll take that out. Don't need that oxygen comment. Don't need... I would keep the trim white space in there because just in case someone types in something weird, but you could theoretically take it out. All this is associated with the LCD screen. That delay and then clearing the screen, LCD screen, not necessary. This is required. Don't need scrolling text message. Don't need any of this. That's all associated with the LCD screen. Don't need this comment. Don't need this comment. This is LCD screen stuff. I can hard code some of these numbers instead of using the constants, just to get rid of that. So 250 for that, 750 for dot duration. I'm just going to take these away for a second so I can see what they are. Word pause is really just duration times 7, so it's 1750 milliseconds. Letter pause is 750. Again, this is not necessary. I'm just taking away a lot of stuff so you can see how the actual code to accomplish code challenge 1 is not that much. Symbol pause is just dot duration, so that's just to the 250 milliseconds. I just keep cutting this so I can look at it as I'm going. Symbol pause again was 250 milliseconds. You can get rid of a lot of these comments just to simplify things up. Symbol pause again, that's going to be 250 milliseconds. This is all LCD cursor stuff. So I actually don't need this one twice. Let's just do that. I actually think all these symbol pauses I have for the LCD. So I'm not sure if I do need them. I'll keep them in for now because I think they're all just associated with the LCD code that I put in. We'll see in a second. Again, if you've stuck with me this long, I'm just showing you how simple this code can be afterwards. I don't need the 2 symbol pauses. I think that's just be true for the LCD. So really, dash duration is just 3 times the dot duration. So 750. This is just associated with LCD screen. So the reason this is 750 is because this is how long you want to hold the dash, the LED high, and this is just the space between symbols, so it's just 250. In case you're wondering why that's like that. This scrolling text is all associated with the LCD, so the rest of this code, these 2 functions are LCD code, I believe. So none of it's required. So that's blink dash, which is blink dash. So there's a lot simpler code here. Blink dash is simply turning the LED high for 750 milliseconds and then turning it low, and then we have a little space between until the next symbol. Dot, blink dot is just turning the LED high for a quarter of a second and then low, and then again the delay between the next symbol. Morse code, a lot simpler like this. This is just the word gap. Again. So yeah, you can see the code a lot simplified. And if I upload that code, make sure I'm on the right port still and I got the right board selected. Upload that code, you'll see that the LCD screen, oh, what do I got here? Okay, I'm using LED pin everywhere. So this is the advantage of why we use constants, because I took out the constant and just decided to hard code things. But this is exactly why we use constants, because when you make a change, say if I was to change this pin from 13 to something else, you have to go through all of the code and make that change everywhere, and you might forget something. This is a fairly simple program, so the odds of me forgetting are pretty slim, but you know, this is a perfect example of why we use constants. I only had to change it in 4 places or more. Let me see here. Or you do stuff like that in 4 places, and it already caused an issue. So I just uploaded that to the program, and now you'll see there's nothing on the LCD screen, but if I send something through a serial monitor, I'm going to send something familiar, hello, because we're all used to that. Dot, 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 4 dots, space, dot for E, space, dot, dash, dot, dot for L, dot, dash, dot, dot for L, and then dash, dash, dash for O. So you can see the code still works. We're just not displaying it on the LCD screen, but you can see how the coding challenge is fairly simple. And I just am horrible at explaining things and took forever to do it. But that's the code for Code Challenge 1 without the convolution of the LCD screen. And that's it. I'll quickly go over, and I say quickly, obviously I know everyone who's watching this video probably thinks that sounds idiotic, me saying quickly. But a couple of the troubleshooting issues you might have had. If you get an error when uploading your code, it's most likely because you have the wrong board selected in the Arduino ID. So make sure you go Tools, Boards, and click the right board. So you'll notice I always went to port and verified what port I was hooked up to, and it was port 16. Also make sure your board selected. If you would have had board Nano selected or Omega or the Mega or something, a different board, do you see how automatically there's an error coming up? If I try to upload that, it just might not work. It'll just be like, it's not the right board. So just wait. So if your code's not uploading, see how it's still compiling sketch, and it seems to be stuck here for a long time. And uploading, access is denied. So I got all these errors. It's because I don't have the right board selected. So again, just want to make sure you have the right port selected, which I do, but you also need to have the right board. So this is not a Nano, this is a Arduino Uno, and so you need to select Uno. And that is, the RedBoard is also an Arduino Uno you would select for that, a generic Arduino board. Anyway, that was an incredibly long video. I thank you for sticking through it with me if you did. Hopefully you kind of got a little more information on circuit 1A, basically getting LED to blink, and more importantly, the coding challenge. And I promise the next videos will be shorter. And I'm getting a call.